Welcome back everyone. In this lecture, we will continue with the study of irreducible representations of sln+1. So, we will actually construct very explicitly irreducible representation that are associated with actually given dominant weights. So, let us actually observe the following. So, here is the very important proposition. So, we can actually use the tensor product in order to actually create new irreducible modules. So, what I mean by that, okay, of course, tensor product of two irreducible is not irreducible, okay. So, that is not that hard to see unless one of them are trivial. But what we can do, we can actually look at this highest weight sub representation inside the tensor product. So, that will actually give us irreducible representations. So, let us actually make it very precise. So, let us say we have k number of highest weight G modules and say they are generated by V1 etc. Vk respectively. Okay, and their highest weights are given by lambda 1 etc. lambda k. So, this is the given data. So, V1 is generated by small v1, Vi is generated by small vi, and the weight of Vi is given by lambda I. So, the weight of small vi is given by lambda I. So, now we can actually look at the tensor product and take this natural element V1 etc. Vk, tensor etc. Vk inside this. Then one can easily conclude that this is indeed highest weight vector, and not only its highest weight vector with the weight lambda 1 plus etc. plus lambda k. So, this is the highest weight vector of highest weight lambda 1 x plus etc. lambda k. So, this just follows from small computation. If you take H acting on V1 tensor etc. Vk, then this is given by H V1 tensor etc. Vk plus etc. plus V1 tensor etc. tensor H Vk. So, H acts as like derivation. So, then this is exactly given by lambda 1 of H plus etc. plus lambda k of H times V1 etc. Vk. So, this is true for all H in H. So, that is why it has the weight lambda 1 plus etc. lambda k. Now, if you compute again x acting on V1 etc. Vk, then you can easily see that again using replace H by x, then H V1 must be 0 and then H Vk is 0, that implies this is 0, and this is true for all x in n plus. So, this proves that this natural vector that we are considering inside V1 tensor etc. Vk, that is indeed highest weight vector. So, if you take the submodule generated by that UG V1 tensor etc. tensor Vk, and that is going to be highest weight representation. But from our previous observation, we can easily see that this must be irreducible module, and this irreducible module corresponds to the highest weight lambda 1 plus etc. lambda k. So, this is irreducible module, of course, associated with lambda 1 plus etc. lambda k. So, this is how one actually constructs all the irreducible representation corresponding to the given dominant weight lambda. So, now let us try to use this. So, if we use this observation, then we can easily see that given lambda, which is coming from lambda plus, one can write lambda as some m1 omega 1 plus etc. plus some m n omega n, where omega I is the fundamental weights. So, which are actually weights inside H star dual to the basis H I. Okay. So, since omega I is actually dual to H I, H S being basis of H, omega I will be linearly independent and it is basis of H star. Okay. So, given any lambda, you can write it in terms of this omega I basis. Now, it is easy to see lambda of H I is m I, those must be non-negative integers. Okay. So, this actually tells you that if you are interested in constructing this V lambda that corresponds to lambda, then it is enough to construct these fundamental representation, which are nothing but V omega 1 etc. V omega n. So, let us say we have constructed V omega 1 etc. V omega n. So, this will be the first step. So, then one can immediately consider this V omega 1 tensor m 1 tensor etc. tensor V omega n power tensor m n. Then if you take this V lambda, so that is going to sit naturally inside. Indeed, this V lambda is given by the submodule generated by the corresponding this weight vectors. Okay. So, V 1 tensor m 1 tensor etc. tensor V k tensor m k. So, this is the way one can construct for any given lambda dominant the irreducible module corresponding to that. So, this indeed proves the existence if we are able to construct this fundamental representations. Okay. So, this is actually kind of very explicit. So, if one works out for type A, which is sln+1, then we can easily see that the fundamental representations can be constructed using natural representation. So, let us consider the natural representation Cn+1. So, this we call it V. So, this is the natural representation of G, which is sln+1. So, we already did the computation. Okay. We can easily see that. So, H I acting on this E1 is going to be exactly epsilon 1 of H I E1. If you think about it, it is exactly omega 1 of H I E1. Okay. And obviously, x E1 is 0 for all x come from n plus, because n plus being all strictly upper triangular matrices. So, if you act it on E1, it is going to be 0. So, this actually tells you that E1 is indeed highest weight vector in Cn+1, but we already verified Cn+1 is actually irreducible representation. So, E1 must generate Cn+1. So, this is actually the generator of Cn+1. So, that means this Cn+1 corresponds to V of omega 1, and I will leave it as exercise to prove the following. So, if you actually work with the tensor product, so there is this natural sub representation of that called symmetric powers. So, if we take the symmetric powers of this Cn+1, then it is naturally isomorphic to V of k omega 1. So, what we need to prove? We need to prove that sim k of Cn+1 is just a highest weight representation corresponding to the highest weight k omega 1. Then from the theory, we know that it must be irreducible representation corresponding to k omega 1. Indeed, if we take this natural generator, okay, so this is indeed submodule generated by this E1 tensor etc. tensor E1 in the tensor product. You take this representation Cn+1, take k number of tensor copies, then inside that you look at the submodule generated by the k tensor E1 etc. E1. So, that will be your symmetric power. So, now one can actually use this. Okay. So, let us actually outline what the computation actually goes here in order to prove this. So, we already know what is the basis of our symmetric powers. Okay, let us recall. So, let us use this notation. So, just denote T of k1 etc. kn by the summation E S1 tensor etc. tensor E Sk, where this S1 etc. Sk, they are all coming from 1 to n plus 1, and the number of I appears in this expression. So, that must be exactly Ki. So, that means number of j's that are equal to, like, let us say number of j such that Sj equal to I. So, that is exactly Ki. in this tuple S1 etc. Sk is K. So, we already seen that if we take all this Tk1 etc. Kn such that this K1 plus etc. Kn is K. So, these elements form a basis. So, this form a basis for this symmetric powers. Because they form a basis, if you are interested in proving that the submodule generated by this E1 tensor etc. E1 is exactly this. So, then you need to actually get all the basis elements by applying this y powers on this E1 tensor etc. En, because this E1 tensor etc. En, that is going to be the highest weight vector, because that is obviously the highest weight vector inside your tensor product. So, you can't use any element from n plus or h to obtain new vectors. So, you have to use vectors from n minus to obtain the new vectors. So, let me just tell you how one actually get the vectors. So, these are all exercise. So, first of all, it is easy to compute the weight of this T of k1 etc. T kn. The weight of this T k1 etc. kn is nothing but k1 epsilon 1 plus etc. plus kn plus 1 epsilon n plus 1. And not only that, so if you take this yi acting on this tk1 etc. kn plus 1. So, this is exactly given by, so it is actually ki plus 1 times something looks like this t only, tk1 etc. ki minus 1 ki plus 1 comma etc. kn plus 1 0 otherwise. So, this happens if ki is greater than or equal to 1. So, basically you just drop the ki and then you subtract minus 1 from the previous one and then add 1 from the opposite one. So, note that the weight should actually kind of should match. Okay. So, basically the yi is going to decrease the weight by alpha I. Okay. So, if you do the computation of weights, you can easily see that the weights matches. So, now using this you can actually get this T of k1 etc. kn plus 1 from starting with this E1 tensor etc. En. Note that this T k 0 etc. 0 is nothing but E1 tensor etc. E1. So, this appears k times. Now, using this you can easily say that the T of k1 etc. kn is obtained by taking this T k 0 0 and repeatedly applying some y powers. So, exactly you will be applying y power n k n plus 1 divided by k n plus 1 factorial, y n minus k n plus 1 divided by k n plus 1 factorial and so on, y 1 power k 2 plus etc. plus k n plus 1 divided by the factorial of that. So, basically you apply these powers to this T power T k 0. So, if you think about it, so these are all the lowering operators. So, we have to apply correct number of times to reach the other vectors. Okay. So, this way you are actually able to go from the highest weight vector to other vectors. So, this indeed proves that if you take this highest weight vector E1 tensor etc. tensor E1 and then take the sub representation generated by that is going to be exactly the symmetric power kth power. And because this highest weight representation is irreducible, so that would imply that the symmetric power is irreducible, and obviously the highest weight is being k omega 1. So, the symmetric power is isomorphic to V of k omega 1. So, this is indeed some other way of constructing the same representation. Okay. So, we have used the tensor products. So, now we will actually construct other fundamental representations. Okay. So, maybe I will state it as a proportion. So, if you take any I which is so let us say any k which is less than or equal to n, then we can look at this alt k c power n. So, if you think about it, so this is indeed isomorphic to V of omega k. Okay. So, alt 1 Cn plus 1 is exactly Cn plus 1. So, that corresponds to V of omega 1, and remaining alt powers you can see that they are naturally isomorphic to this V of omega k. So, what does it mean? It means alt k Cn plus 1 is indeed highest weight representation corresponding to the highest weight omega k. That is all we mean, and irreducibility comes for free. Okay. So, how one can prove this? Again I will actually outline the proof. So, we already have the basis. So, basis is given by, let us call it this u I 1 etc. u I k. So, this is given by summation sine of sigma, sigma comes from Sn plus 1 E I sigma 1 tensor etc. tensor E I sigma k. So, this is going to be a basis. So, when you take the indexing set to be I 1 less than I 2 less than etc. less than I k. So, because there should not be any repetitions. So, if we take these tuples and then run it over all these tuples u I 1 etc. u I k. So, that will form a basis for alt k C n plus 1. So, that is obvious. So, now it is easy to compute what is the weight. The weight of this u I 1 etc. u I k is given by epsilon I 1 plus etc. plus epsilon I k. So if you are not comfortable with this, just put bar everywhere, okay, because we are computing only the h weights. The same computation actually works for dou n plus 1 weights, okay, there is no difference. So now what will be the weight of u1, 2, etc. k? So that is going to be exactly epsilon 1 plus etc. epsilon k, which is omega k. So it's not hard to prove that u1 etc. uk is a highest weight vector. So that's a simple exercise, okay. So this is again simple enough to prove. So what is difficult is indeed getting all other elements ui1 etc. uik from u12 etc. k using the lowering operators, okay. So the way to get it, I will just write the formula, then you can actually verify. So if you take this ui1 etc. uik, which can be obtained from u1 etc. uk by applying these successive lowering operators. You take yi1 minus 1, y again I1 minus 2 and so on up to y1 times y I2 minus 1 and so on y up to y2 and so on, you go all the way to yik minus 1, yik minus 2 and so on yk, and then you apply it on this vector. Note that I1 being strictly less than etc. strictly less than ik, that implies I m is greater than or equal to m, okay. So that is why you are going from I1 minus 1 to all the way to 1 and then I2 minus 1 to all the way to 2 and so on. So if you take this vector and then successfully apply these lowering operators, so then you are actually getting this vector, okay. So that tells you that this alternating power is obtained as highest weight representation. The alt k of the Cn plus 1 is naturally sum of it to V of k omega 1, sorry, V of omega k. So now if you are interested in constructing the general irreducible module corresponding to given lambda. So if you take lambda being dominant, then you can write it as I said m1 omega 1 plus etc. plus mn omega n. Then consider this alt 1 Cn plus 1 power, again the tensor m1 tensor etc. tensor alt k Cn plus 1 power mk tensor alt n plus 1 Cn plus 1 power tensor mn. So up to this n. So when you take alt n plus 1, then that becomes actually the trivial representation, okay. So up to n it will be this. So you consider the tensor, then consider the highest weight tensor product of highest weight vectors inside this tensor, then that is going to be isomorphic to V lambda, okay. So this way we proved existence of given. So this proves the existence of V lambda. Okay. So, indeed if you actually think about it, the examples that we have seen, so the trivial module corresponds to V 0 and Cn plus 1 corresponds to the omega 1, and the dual of this indeed corresponds to. So, if you identify with epsilon 1 basis, then this is V of epsilon 1, then this corresponds to V of minus epsilon n plus 1. Okay, that is the dual. So, now if you take sln plus 1, which is the adjoint representation, so that corresponds to indeed what is called the highest root. So, which is epsilon 1 minus epsilon n plus 1. I am writing everything in terms of epsilon a basis. Okay, you restrict to h. So, now if you take this alt k c n plus 1, if you think about it in terms of the epsilon a basis, then this is exactly equal to V of epsilon 1 plus etcetera plus epsilon k, okay, which is same as a sln module V of omega k. Okay, so this is the translation between the epsilon a basis and the thing. So, now actually this is actually gives us a very explicit construction in terms of the tensor products. But D.N. Verma indeed proposed some abstract way of constructing these irreducible modules. So, he introduced what is called Verma module, and then he actually identified all these irreducible representations as quotients of Verma modules. So, we will be actually seeing that construction as well. That construction actually can be done for any lambda, not necessarily lambda being dominant. So, note that in this construction we have used the fact that lambda being dominant, because we need to take the tensor powers, okay, corresponding to this mi's. So, mi's being non-negative integers used very much, otherwise we will not be able to consider this tensor products, okay, the corresponding tensor products. So, but D.N. Verma proposed this idea of Verma module, which actually can be defined for any lambda in H star. So, for any lambda in H star, we define these Verma modules. So, which will be defined to be actually highest weight representation of highest weight lambda. So, but this is somewhat universal highest weight representation. So, these Verma modules are the universal highest weight representations associated with lambda. So, which we call it z of lambda. Okay. So, then one can actually prove that there is unique irreducible quotient of z lambda. So, there is an unique quotient of z, unique irreducible quotient of z lambda, which we call it V lambda. So, which is denoted as, and of course, there should not be any confusion between this lambda being dominant and so on. Okay. If lambda is dominant, then we will prove that this V lambda is indeed finite dimensional. So, since it is finite dimensional, so this will be naturally isomorphic to the irreducible module that we constructed before. Okay. So, we indeed established this one-to-one correspondence. So, from lambda plus 2, the set of all irreducible 5-dimensional representations of sln plus 1 modulo the isomorphisms. So, the map is given by lambda goes to the bracket V of lambda, and we already proved that this correspondence is one-to-one correspondence. Okay. So, now Verma actually introduced this Verma module in order to construct this irreducible highest weight representation for any given lambda in H star. So, that is the beauty of Verma's construction, and that universal construction indeed allows us to actually to deal with some infinite dimensional irreducible module. Okay. So, indeed we will prove that it is a theorem that these V lambdas coming from these Verma modules, they are finite dimensional if and only if the lambdas must be dominant weights. Okay. So, this is indeed a very deep theorem that we prove in the coming classes. Okay. So, this is where we are heading with the 5-dimensional theory. Okay. So, this Verma construction is somewhat very subtle and important, because that construction works for any semi-simple algebras. I will stop here. We will continue with Verma's construction in the next class. Thank you.